At the darkest depths of the ocean, the biggest predators disappear, and the creature responsible is an animal that, almost anywhere else, would be prey. At 10,935 meters beneath the surface of the Pacific Ocean, the water pressure is so immense it would crush a submarine's hull in seconds. By all logic, only a handful of scavengers should be able to survive down there. But within a narrow band of the Mariana Trench, between 7,000 and 8,000 meters below the surface, something completely defies the rules of the natural world. For a long time, biologists assumed these giant amphipods were scavengers on a large scale, bigger versions of the same thing amphipods do everywhere else. Wait for something to die, wait for something to fall, then eat. That assumption started to fray when the researchers began looking at what was inside their stomachs. Because what was inside their stomachs was not just carrion, it was fish, fresh fish, snailfish that had been alive not long before the amphipods got hold of them. Snailfish are the vertebrate rulers of the deep trenches. They hold the record for the deepest fish ever filmed alive, spotted at more than 8,300 meters down in a different trench off the coast of Japan. They have translucent, gelatinous bodies, tiny eyes, and skulls that are only partly ossified so that pressure can pass through them without cracking anything vital. In most of the hadal zone, snailfish are the top vertebrate predator. They eat the amphipods. That is how it is supposed to work. Small crustaceans on the bottom, larger fish above them, everything organized by size and speed the way it is everywhere else on Earth. Except in this one zone, in this specific corridor of the Mariana Trench, the roles reverse. The amphipods here are big enough, numerous enough, and coordinated enough that they overwhelm the snailfish. They swarm. They arrive in numbers that no fish, however well adapted, can fight off. And a snailfish that has spent its entire evolutionary history at the top of the local food web finds itself in this one zone at the bottom. To watch it happen on the footage that has come back from crude submersibles and baited lander cameras is genuinely disorienting. A snailfish glides slowly across the sediment, its body undulating in that ghostly, weightless way that hadal fish move. It approaches what looks like food, and then the sediment itself seems to come alive. Hundreds of amphipods, sometimes thousands, rise from the seafloor and converge. The fish tries to turn. It cannot turn fast enough. Within minutes, there is nothing left but a stripped skeleton, and even the skeleton will be gone before the next tide of currents passes through. This is not an isolated event. Researchers who have dropped bait cameras into this zone have watched it repeatedly, and the same footage has shown something else. It is not only the snailfish that go down this way. Larger scavengers that occasionally wander into the zone from shallower waters, deep-sea holothurians, drifting cephalopods that have descended too far, even the corpses of much larger animals that fall from above, all get processed by the same swarm with the same relentless efficiency. The middle zone of the Mariana Trench does not tolerate large predators. It converts them into raw material. The question is why? Why here? Why this specific band of the trench? Why not the deeper Challenger Deep, where amphipods also exist but do not appear to form the same overwhelming swarms? Why not the shallower abyssal plains, where snailfish and other fish comfortably rule? Part of the answer, it seems, is chemistry. The middle zone of the trench sits on top of an unusually active band of methane and hydrogen sulfide seeps. These chemicals leak up out of the seafloor from the deep crust below, where the Pacific plate is grinding down beneath the Philippine plate in the slow-motion violence of subduction. When those chemicals reach the water, they feed the microbes we now know populate the trench in extraordinary numbers. And those microbes feed the tube worms, the clams, the bivalve beds that stretch for hundreds of kilometers across the trench floor. The result is that this middle zone is not a food desert. It is a food factory. Chemosynthesis, the process by which microbes pull energy out of chemicals rather than sunlight, produces enough biomass here to support a dense population of small animals. And amphipods, being generalist eaters, take full advantage. They graze on the microbial mats. They pick through the clam beds. They eat the drift of dead material from the surface. And they grow. In a place where food is abundant in ways nobody expected. They grow to sizes that let them do things amphipods elsewhere cannot do. But abundance alone does not explain the reversal. Abundance produces big animals in many places. It does not usually produce a food web that flips upside down. The other half of the answer appears to be about the snailfish themselves. And this is where the story becomes uncomfortable for anyone who wants a clean explanation. Snailfish are extraordinary animals, but they are extraordinary within a narrow range. The proteins in their tissues are folded to survive under specific pressure conditions. The chemistry that keeps their cell membranes flexible works best within a specific temperature band. Push them into slightly different conditions, and their advantage disappears. In the middle zone of the Mariana Trench, the water carries a slightly different chemical signature than it does elsewhere in the Hadal zone. The sulfide levels are higher, the oxygen levels are marginally lower, and for reasons that researchers are still working out, snailfish in this zone appear to be operating at the edge of their physiological limits. An amphipod, by contrast, is chemically less picky. Its exoskeleton, reinforced in some species with aluminum extracted from the surrounding sediment, resists the corrosive chemistry of the seep zones. Its metabolism is simpler and more forgiving. Where the snailfish struggles, the amphipod thrives. And when a fish is already stressed, already slower than it would be at its optimum, already working harder to keep its cellular machinery running, it becomes vulnerable in ways it would not be somewhere else. The predators of this zone, in other words, are not stronger than the snailfish. They are not faster. They are not smarter. They are simply better tuned to the specific chemistry of this specific place. And in a food web, being better tuned is often all that matters. There is something else happening here too, something that took longer to notice because the cameras were focused on the drama of the swarms. When researchers began pulling amphipods up from this zone in numbers, they found that many of them carried gravid egg sacs. The females were breeding at rates far higher than amphipod populations at comparable depths elsewhere. The middle zone was not just a hunting ground, it was a nursery, which meant the swarms were self-sustaining in a way that most deep-sea predator populations are not. Every fish that fell to them fed a generation that would grow up to hunt the next. Try to picture the scene as the submersible lights sweep across it. A flat plain of dark sediment, punctuated by the pale swaying stalks of tube worms. Beds of clams packed so densely the seafloor looks tiled. Faint white mats of microbes glowing against the black. And moving through it all, at every level, the amphipods, some the size of a fingernail, some the size of a hand, some the size of a small mammal, all of them slow and patient and endlessly hungry. When something large enters the frame, whether it is a snailfish or a drifting octopus or the sinking body of a shark that died in the sunlit ocean 100 kilometers away, the response is immediate. The swarm rises, the animal is surrounded, and the corridor claims another meal. What makes this zone particularly strange is that it appears to be geographically bounded. Move a few hundred meters shallower into the upper Hadal transition, and the snailfish are back in charge. The amphipods there are smaller and less aggressive, and the food web organizes itself the way food webs are supposed to. Move a few hundred meters deeper into the true abyssal reaches near the Challenger Deep, and the biomass drops off. There is less to eat. The swarms cannot sustain themselves. The system reverts to something closer to the classical picture of Hadal life, sparse and scattered and quiet. But in this middle band, for reasons that combine chemistry, geology, and evolutionary tuning in ways researchers are still untangling, the normal rules do not apply. It is a zone where being large is a liability, where being a vertebrate is a liability, where speed does not save you, and armor does not save you, and the only successful strategy is to be small, to be many, and to be adapted to a chemistry that would poison almost anything else. There is a temptation, watching the footage that has come back, to describe what is happening here as violent. It is not really violent, it is patient. The amphipods do not chase, they do not stalk. They wait, embedded in the sediment or drifting just above it, until something enters the zone and stays too long. Then they converge. There is no drama in the way. There is drama when a shark takes a seal. There is only the slow arithmetic of a food web that has organized itself around one specific fact. In this place, At this depth, the small animals win. The researchers who have studied this zone most closely are careful not to overstate what they have found. They point out that the trench is still poorly sampled, that the middle zone has been visited by only a handful of expeditions, and that what looks like a stable inversion of the food web might turn out, with more data, to be a seasonal phenomenon or a localized quirk. The Huddle Zone is a place where scientific caution is warranted, because almost every time researchers have made confident claims about it, further exploration has forced them to revise those claims. But the pattern is consistent enough now, across enough separate expeditions, that it is difficult to dismiss. The middle zone of the Mariana Trench is a place where predators become prey, where the animals that dominate elsewhere are eaten, where the food web runs upside down compared to almost every other environment on Earth. And the implications reach further than this one trench, because the Mariana is not unique. There are other Huddle trenches around the Pacific Rim: the Tonga Trench, the Kermadec Trench, the Philippine Trench, the Kuril-Kamchatka Trench, and each of them has its own chemistry, its own geology, its own patterns of seep and sediment. If the Mariana can produce a zone where the food web inverts, there is no reason to assume the others cannot. There may be corridors like this one in every deep trench on Earth, unstudied, unmapped, running their strange arithmetic in the dark. What we know about the deep sea is a small fraction of what is there. The 2,550 kilometers of the Mariana Trench have been sampled at only a handful of specific points. Between those points, kilometers of seafloor remain unseen. The zone we are talking about, this corridor where the food chain flips, is one particular stretch that happens to have been visited by the right cameras at the right depth. Other zones almost certainly exist, and other reversals almost certainly happen, and most of them are still waiting for someone to drop a lander into the right patch of darkness at the right time. There is also the question of what this tells us about the general logic of ecosystems. The idea that food chains have a natural shape, with large predators at the top and small organisms at the bottom, is one of the oldest concepts in ecology. It was built from observations of terrestrial ecosystems and shallow marine ones, and it has been taught in classrooms for more than a century. The middle zone of the Mariana Trench suggests that this shape is not a law of nature. It is a pattern that emerges under specific conditions, and when those conditions change, the pattern changes with them. In this one place, in this one narrow band of depth and chemistry, a different pattern has taken hold. Small, numerous, chemically tolerant animals sit at the top. Large, specialized, physiologically stressed vertebrates sit at the bottom and often end up inside the amphipods that were supposed to be beneath them. There is one last thing worth noting. When researchers examined the tissues of the amphipods pulled from this zone, they found, among all the expected biological markers, the same thing that has been found in almost every deep-sea animal sampled in the last decade: microplastic fibers, concentrations of persistent industrial pollutants that in some cases exceeded what has been measured in coastal estuaries in industrialized countries, chemicals that were manufactured on the surface, banned decades ago in many places, and which have nevertheless found their way through 11 kilometers of water column to settle into the bodies of animals that never come near the sunlit world. The amphipods of the middle zone are, as far as anyone can tell, the apex predators of one of the strangest ecosystems on Earth. They are also carrying inside them the chemical signature of a civilization they have never encountered and will never encounter. Whatever else the corridor is, it is no longer isolated. The line between what we do up here and what happens down there has already been crossed, and the crossing is now measurable in the tissue of every animal the trench produces. The snailfish still swim through the deeper reaches, where the amphipod swarms cannot follow. The tube worms still sway in currents too faint to feel. The microbial mats still glow faintly white in the perpetual dark, and in the middle band of the trench, where the chemistry is just wrong enough for vertebrates and just right enough for something else, the swarm waits. It has been waiting there, in some form, for longer than there have been human beings on the surface of the Earth, and it will keep waiting, patient and hungry, for as long as the seeps keep leaking and the currents keep bringing food into range. The strangest thing about this zone is not that it exists. The strangest thing is how narrow it is. A few hundred meters higher, the world makes sense again. A few hundred meters deeper, the world empties out. Only in this specific band, only under this specific set of conditions, does the food chain forget which way is up, which raises a question the researchers have not yet answered, and perhaps cannot answer, with the tools we currently have. If this can happen here, in the most extreme environment on Earth, in a zone that emerged from nothing more exotic than the chemistry of methane and the tuning of a few crustacean proteins, then what other rules that we think we understand are only true within the narrow ranges we have bothered to look at? The trench does not tell us. The amphipods do not tell us. They only continue doing what they have always done, in the one place where being small is the greatest weapon of all.